recording. And this is still visible, right? Probably that's why people are not coming in class, because I used to ask, is it coming? Then they have to see this. Then they are mobile, like two things. Okay. So today we are going to start the one important topic, which is a small topic only, but let's see how far we can do it. So this is technology scaling. Okay. So technology scaling, all of you are aware of that. Like from 1960s, actually transistor has been invented in 1947, right? But say for some commercial application, say starting from 1916 till you can see it is maybe around 2015 up to this graph, what it shows is that is the minimum feature size, right? Minimum feature size means earlier it used to be the gate length. So minimum feature size, you can see this is in log scale. So please note that this is in log scale, right? So minimum feature size in microns, this is like hundreds of micron. This is tens of micron. This is 1 micron. And this is below micron, means the submicron, right? So the transistor feature size has reduced drastically, right? Every year it has been reduced, right? Then how we will decide then how to scale, means like from here to here, should we reduce the gate length by half, 30%, 70%, 80%, how, right? That is one thing that we should know. And what are the advantages, why we actually scale? One is obvious, that is we want more number of devices in the same area, right? We want to increase the device density, right? So that is one obvious advantage for that, right? So is there any other advantage in terms of like power, in terms of delay? Okay. Yeah, can you please speak because of right, right. So we'll also see that whether what is the requirement, whether should we scale down the VDD at the same time, or is there any possibility that we can keep this VDD constant and only scale the dimensions? Okay. So with this brief introduction, so let us then, obviously you have understood one thing, that there is something called the scaling factor, right? So scaling factor means earlier suppose the gate length is 1 micron. So now the gate length would be 1 by S micrometer. And obviously S has to be greater than 1. Right? That's how you make scaling. Otherwise, you will go to the opposite direction. Your devices will be wider. We don't want that. So regarding that, there is an old paper, research paper, and it has been published in IEEE Journal of Solid State Circuits. You see the year 1974. Okay, here the first author is Robert Dinard. Okay, this is called this Dinard rule, scaling rule. They have suggested some rule how devices should be scaled, okay, for the future generation. Right, so we will discuss based on that only what they have suggested, and then we will see what are the changes that we have to do later on. So they have proposed couple of things. The first thing that they have proposed is called constant field scaling. Okay, so in constant field scaling, what we will do, we will make the field constant. Okay, means if you are changing the, for example, see here we have first consider these two parameters. Here it is L, W, T, ox, XJ, right? So all are okay. What is L? Gate length. What is W? Gate width. What is T, ox? Oxide thickness. What is WJ? WJ is the junction depth. Okay, this junction depth. I will show you in the next slide, means next page, what do you mean by junction depth. So all are these physical parameters. So here, all the physical parameters here is been scaled by a factor of S. So that means into 1 by S, right? We are scaling it, right? At the same time, we are also scaling VDD, also by the same factor 1 by S. Then what will happen to the electric field? Electric field is voltage by distance. So we are scaling the distance by same amount. We are scaling the voltage. So what will happen to the electric field? Electric field will remain constant. So that's how the name has come, this constant field scaling. Fine. So during, okay, why we need that constant field scaling? Because if we keep this VDD constant and only reduce the like gate length and this S, the source and drain distance and all these things, then what will happen? Then there is an property of each material which is called the breakdown electric field, right? Once that breakdown electric field will be achieved, then device will be permanently damaged. So we cannot do that. Okay, so let's first focus primarily on this only, constant electric field only. Then we'll see other variations. Okay, now we understood here one thing, that is in constant scaling, constant field scaling or constant electric field scaling, how we are going to scale the physical length as well as the supply voltage and VT. VT is the threshold voltage. Then from this, can you tell me like what will happen to the device area? Reference, let me. Yeah, what will happen to the device area?
1 by S square.
1 by square, 1 by S square, right? Ah, I have written it in the difference. Yes. So it is 1 by S square. Okay. What will happen to the substrate doping? Maybe if let me check who can comment on that. What will happen to the substrate doping?
It can remain constant.
It will remain constant? Probably no, because okay, let me show one diagram. So this is the MOSFET typical structure, right? This is with length, source, drain, gate. Acha. XJ we have mentioned earlier. This is the junction depth. So this is the junction depth, right? So when you scale this L, this junction depth has to be also scaled down. Okay. Okay. So now what we are saying? We are saying that we have reduced this L to L by S, width to W by S, VDD to VDD by S. Then we are commenting then what would be the doping concentration for the new device. Okay. See, this is an PN junction. This is an PN junction, right? So PN junction, if there is an PN junction, then PN junction also has some depletion width, right? So we are scaling all the physical dimension. So that means this width also has to be reduced, right, by the same amount, right? Then are you getting my point? Otherwise, what will happen? You think about think about this case. So I'll say now the depletion width is like this. Here the depletion width is like this. Now you are scaling. Then if the depletion widths are remain same, then what will happen? Between the gate they will touch, right? And there is no neutral region, right? Is this depletion region and this depletion region will be like merged, and then you lose the transistor operation, right? So you have to scale this WD also. Then what is the relation of this WD? WD, okay. What is this doping concentration of the source or drain side? Very high, in the range of 10 to the power 20. So probably we cannot change here, right? It is very high doping. We need very high doping in this, right? So where we can change? We can change probably here, because this is the body doping. This is quite light. Okay. So say earlier the doping concentration was Na, right? So this is a single-sided PN junction. Means basically this is N plus P junction, right? And for N plus P junction, we know the equation of depletion region is 2 epsilon I V by Q into Na, right? Okay. So here we have to find what should be the value of Na. So let us keep this Na. So that gives us this equation, right? Okay. Now let's see from here what we can comment on it. So 2 epsilon of silicon is the property of silicon. We cannot do anything. But what we can do on V? Yes, we are scaling V to 1 by S. Q is the electronic charge. We cannot do anything. W is this WD, right? WD also we have to scale equally by 1 by S. Then what will happen? This become 1 by S square, right? Then what is going to happen to this N? It has to be increased by S times, right? Then this will also scale by like then WD also will scale by WD by S, right? You understand from that point? Okay. So here substrate doping we have to change by S times. Okay, what will happen? COX. COX is that COX in the equation which is per unit area ID equation. What will happen to COX? COX is what? Epsilon ox by Tox. Epsilon ox not changing, right? So it is basically COX equal to epsilon ox by Tox. COX is not, epsilon ox is not changing. Tox is changing by 1 by S. So it will increase by S. Okay, what will happen to the total gate capacitance? Means COX into area. So it is basically COX into area. Area is W into L, right? COX is increased by S. W is increased by W will become 1 by S. This become 1 by S, right? So then the total gate capacitance is actually reduced, right? But if you see the capacitance like density per unit area, that is actually increasing, right? Okay. Now next question is what will happen to the ID? ID is the drain current. Okay, so I have written, I do not have sufficient space there, so I have written it here. So this is the drain current, right? We are assuming that mu n is not changing. Let's say that mu n is not changing, mu n will also change, right? But that is not this type of proportionately, and that is a bit complicated. For the time being, we are considering mu n constant. COX is changing by S. W by L, it is a ratio, so it's gone. V, voltage is changing by 1 by S. So it is 1 by S square. So it become 1 by S, right? So ID become 1 by, means 1 by S, right? Okay. What will happen to the current density? Current density means current per unit area. See, here we are getting less current, that is true. But at the same time, we have to also understand that our area has also reduced, right? So from that point of view, let us find for per unit, from the per unit area point of view, how much current we are getting. So it is ID by area. So ID is scaled by 1 by S, this by 1 by S, this by 1 by S. So that makes this current density is actually increased by S, right? And S is greater than 1. So the current has actually been higher compared to the previous one. Okay. So the current is this S. No, current is 1 by S, right? This current density is S. What will happen to R on resistance? You remember? Device on resistance. So we have done a simple calculation, right? For how do we find on resistance of PMOS or NMOS? That, you know, the resistance, average resistance from this point and this point, right? And again, this average resistance between these two again depends on this ID sat, right? And this VDD, right? So it is resistance. Resistance is V by I. So again, it is V by that formula, V by I. So V is changing by 1 by S. I is changing by 1 by S. So R1 has, let me also, yeah, right. So it has remained, R1 has remained the same. What will happen to the intrinsic delay? Let us say that intrinsic delay we are defining by R1 into C gate. R1 into C gate, right? On resistance R and the gate resistance. We are not considering the parasitic capacitances. Okay. So if that happens, then what will be the case? C gate is the total gate capacitance. So R on remains same. C gate has become 1 by S. 1 by S. So this has become 1 by S. So here is one of the beauty of scaling that probably you have noticed, that the intrinsic delay, you don't have, see, have we thought of anything like we want to make this intrinsic, make the device faster? No. What we have done, we have just followed one simple technique, just let us reduce it. And at the end of what we have end up with, that the device is actually getting faster, means the intrinsic delay is getting actually reduced, right? You don't have to do anything else. Just reduce all the dimensions equally and you will get an speed up as a result, right? So that is another criteria why we should go for scaling, right? And obviously this is from the device point of view. Now think from the circuit point of view, architectural point of view. Okay, when you are trying to make an very high speed devices, then obviously you have some architecture level of design that is in your hand, right? Circuit level of design that is also in your hand, right? So the overall gain in terms of speed will be much higher than this 1/s. So this is just in terms of device level. Are you getting my point? Okay. Then what about power? What about power? Power is basically I into V. What will happen to I? I is 1/s. What will happen to V? 1/s. So that way, then power becomes 1/a square. So again, one of the important thing, right? These two are like two of the major metrics, right? Parameter for us in digital design. One is the delay and the other is the power. So you can see just by scaling the device down, we can also significantly reduce the power by, and now this time it is 1/a square. Again, this is from device point of view, architecture, circuit, that is in your hand for a designer. Then there is one more term which is called the power delay product. It basically gives the power and this delay, right? The product of these two. So here this power is become 1/a square and delay become 1/s. So in terms of power delay product, you see it is 1/s cube, right? Then, but so I hope that you are getting this, my what I'm trying to say, right? Just by simply scaling down the device, you can achieve so many things. Okay. What about the power density? Power density is this power by area, right? Power by area. So it is basically 1/a square. Area also scales by, you can see here we have done 1/a square, right? So it is 1/a square. So it become 1. So the power density, that means from the that area point of view, the power, radiated power, that will be remain the same, right? But from the device point of view, but that power has reduced. When the single device is taking less power, but if you consider the area wise, that is consuming the same amount of power, right? Because now in that area you have more number of devices, right? Earlier one device was radiating P power. Maybe now suppose more devices will radiate the same P amount of power, right? Okay. So with this, then let us see one more thing. Then we'll come back to this chart again. Then the here one relevant question should to be asked is that what is then should be the value of S, right? Okay. Now the answer is this typically this S has been considered as like around 1.428, so that 1/s, that means the reduction is nearly equal to 0.7. Now, okay, why this number? Okay, why this number I will come, but let's see the what is the advantage. Okay, if we have 1/s equal to 0.7, say we have two devices. Okay, this is the old generation device, this is the new generation device. Old generation, for a single MOSFET, we have area is L into W, so it is WL. Now for the new generation device, the area is 0.7 W, 0.7 L. So that becomes 0.49 WL. So what you can see if you compare these two, the area is reducing by, the area is becoming half, right? Are you getting some relation with this, with the Moore's law, the famous Moore's law? You know Moore's law? No? Okay, maybe I will show some another diagram in the Moore's law. Okay, if you're not getting, fine, but you are getting one definite one relation, that if you choose this one, the scaling 1 by s to be equal to 0.7, then the area become half. Okay. Then what will happen to the density, means the chip density or device density? That becomes simply doubles, right? Okay. Now, from industry, in industry, this factor that 1 by s is equal to 0.7 has been considered from a very, very long time. Okay. Because from one generation to other generation, when you go, right, one generation to the next generation, your number of devices in a chip is actually double. Okay. So let us give you some another perspective from here point of view. We will come to this later on. See, this is some of the scale, some of the technology nodes. Okay. So maybe you are familiar with 180 technology node. Are you familiar with that? Right? We have discussed. Okay. Then what will be the next technology node? You will get the next technology node by multiplying 180 into 0.7. Please tell me what is the result?
126.
126 nanometer, right? See, the next technology node, generally it means they do not make it 126. They try make it type of round of the type of thing. So here you can see that next the next technology node is 130. Okay. So if you have to go to the next node, see again 130 into 0.7. 100, 109. So it is 109. 91. Okay. So it is 91 nanometer. So here you can see it is 90. Right? The technology node is 90. So you can again multiply with 0.7. You will get 65 like that. Okay. This is how the technology node used to be earlier. Again, I'm saying earlier, not now. Okay. Where is the difference and what do you mean by technology node? We will come a bit later on. Okay. But you have understood like how the industry is following. The industry is following this rule. 0.7, 0.7, that makes the area hub, and that means the device density increases in the next generation chip. Okay, so we'll come back to this slide after some time. Okay, now the question is, then what is, why this 1 by s to be equal to 0.7? Okay, so that means we are reducing by 70%, right? We are reducing the dimension by 70%. Why not 30%? Why not 20%? Yes, we can actually opt for 30%, 20%, 25%, whatever be the number we want, we can do that. But there is also one more important thing, that is the time. Okay, this is from the device fabrication point of view, it is not so easy to go just to reduce all the dimension by 50%, 40%, 30%, whatever we want. That takes a huge amount of time for the fabrication, optimization, processing, which material to which material you go. You can have it, but then what will happen? Suppose now Intel is launching some chip, right? Maybe after 10 years, Intel will launch another chip, which you might be now 10 times faster than this one. But think about Intel's business between these 10 years, right? So every year, like, after 1 or 2 years, they will make this type of small, like 70% reduction, and you get like some type of improvement, and they release it. Then they next process it, then they next process it, then they next process it. Because for this research and development, funding should also come. Where from the funding will come? When people will buy, there, some part of the funding is also there, right? Right? Should be the self-sustainable loop, right? So that's why, if it's not impossible, it's possible, but you have to also see the whole ecosystem, right? If you consider that ecosystem, then that is not sustainable, right? So that is the number, and that is why it is like 0.7 industry have fixed, and this actually resonates with Moore's law. Okay, maybe in next class we will see that what is Moore's law, and then we'll try to understand. Okay, Moore's law actually is a not type of any physics based law, though we call it law, It is a observation based on few points. Okay. And then the industry has worked hard to make the law correct. Okay. He says, like, suppose after 2 years, the number will become double. There is no like physical reason behind it. So industry has taken it as a standard. So, okay, this is our goal. So we have to make this thing happen. So that's how it became a law. And so far it is still valid. Understand? Okay. Then why not 90%? Some of you say, like, when the, see, if you can make it 90%, then the 90% this increment is quite incremental. Then if I have some mobile today and after 1 year, company launch another mobile, which is say just 10% faster in speed. Should I be worried to buy that? Probably no, right? So that is another thing. That's how this trade-off has come, and people have fixed it to 0.7. Right? Okay. Then, so we have understood this constant electric field scaling. Okay. Now the next one is here. One thing is that is important is that we have discussed that VDD or VT, we have to scale it by 1 by S, right? But is it really possible? So that means today you are working on suppose 3 volt. After 2 years, when you launch it, the new one, okay, you have to make it this 3 by S, right? Whatever be the X factor, right? Then all the architecture, all the peripheral device, everything has to be changed, right? So even though you want this thing to happen, but there isn't quite resistance, okay, for that. People do not really want this voltage, this VDD voltage to be scaled down very significantly, right? Not eventually to this threshold voltage as well. Because you know what will happen, I have shown you one earlier, there is something called subthreshold leakage. If the threshold voltage becoming very, very low, then it is becoming very hard for, by applying some gate voltage to turn the device off. You have lots of leakage current, so there will be lot of power dissipation in terms of leakage. So as a result, there is some, resistance for this VD and VT scaling or the voltage scaling. So this is one like, this is one community who want this. There is another community, okay, who said that, no, we will not at all scale the voltage. We will scale only the dimensions. Okay, they're a complete opposite community. Okay, so if we do that, then quickly write like what will happen. So here this become 1 by S. VDD we are not scaling. So what will happen to the substrate doping? Substrate doping become, you can calculate it. I think it will become A square. Okay, I'm just writing it from this here. So it become 1 by device area become 1 by A square. C aux become S. C gate become, no, I think this S square 1 by S. C gate become 1 by S. Then ID. This ID become 1. Please check it though. Okay. ID become 1. Drain current density become, ID will become S.
Sir, ID becomes S.
ID become S. Fixed voltage scaling, should it be? ID become S?
Because Cox increases by S.
Cox, Cox increases by S. True.
So W by L is constant. VGS minus VT is
Okay,
constant.
okay, let us see that. So here Cox is increases by S. W by L is this one. So it become S. And I do not know why they have written here 1. Okay. So this S square, then if you opt for R1 become S. Or drain current become, then it will also change. It will become S cube. Okay. Then R on. I think you can do it, right? You understood. If you have understood for this, you should be able to do it for this. There is no new funda here, right? Okay. So now Okay, so you have understood this part. Okay, now let us see that is it really true in terms of what history has said, means what history says, like from different channel lengths, how far these things are true. So this is an, okay, this source is IEEE. Okay, this is from one of the journal from IEEE. So here it shows the voltage, okay, both VDD as well as this VT, threshold voltage, for different channel lengths. And you can see both are in log scale, right? Okay. So here you notice that here this, when the gate length was 1 micron, then the voltage, supply voltage used to be 1, 2, 3, 4, around 5 volt, right? This is around 5 volt, right? This point, right? Now we are reducing it to 10 times. So now it is becoming 100 nanometer, right? So at 100 nanometer, what is the voltage say? Say 1.5. How much reduction? From 5 to 1.5, right? Whereas what is the reduction in terms of this device dimension? 10 times. And here around 3 point, like more than, little bit more than 3, right? This type of reduction. So you can clearly see that even from the history also there is an resistance for this VD scaling, because if you are changing VD, you have to change VD for all the peripheral architecture and all these things. Similarly, you can see for VT also the same. See VT, for when it is 1 micron, VT used to be around say 0.8 volt, right? Then it has become 100 nanometer, and in 100 nanometer the VT has become 0.1, 0.2, 0.3, 0.35, and it will be really hard to go beyond this VT. We really cannot go beyond this. Now it has type of getting and stagnant. VT threshold voltage we cannot reduce further. So similarly, then VDD also we cannot reduce, because this is the overdrive. You understand the overdrive? It is VDD minus V threshold voltage. That will come in terms of this I square, right? Means I. This I is basically this square. So history also says the same thing, whatever we have discussed. So depending on that, then people have proposed another scaling technique, which is called the general scaling, where people have said, like, we will scale this length and VDD with some different scaling factors. For this is 1 by S, for this it is say 1 by U. Okay, so now you can obviously say which one should be higher, right? Obviously this should be more aggressive. The scaling of this length and the physical dimension should be more aggressive compared to the voltage scaling, right? Okay. Then if this is the technique, then I think you can also feel for the rest of the things, right? Okay. Then let us come to this different technology nodes. Okay. So technology nodes means what? I think you have, you have heard it quite enough, right? It is 22 nanometer technology in mobile phones. Snapdragon processor, they are using 10 nanometer technology, 7 nanometer technology, right? And then if the number goes, number becomes smaller and smaller, then that gives an impression in our mind. Then our processor is very fast, right? That is the impression, right? Now let us try to understand what do we mean by technology node. Okay. So in technology node, I'm just reading from here. This technology node, also known as the process node or process technology, this refers to the semiconductor manufacturing process and design rules. Different nodes. Okay. So typical important things I will just highlight here. Yeah. Historically, the process node referred to the number of different features for this transistor, including gate length. Let me just, okay. So earlier, when I say that gate length is, 1 micrometer node, so that means gate length was actually 1 micrometer. When I say 500 micrometer technology node, then that become, gate length become 500, not micrometer, sorry, 500 nanometer, 500 nanometer technology node, right? Then afterwards, what happened? It was very difficult to scale that gate dimension, as per the technology node. So then people have shifted to the other technique. They have said, like, now we are changing our nomenclature. We will say technology node or define technology node by the separation between the metal layer 1. What do you have you understood by what do you mean by metal layer 1? You think of so many MOSFETs, okay, at the ground level, right? They has to be connected with each other, right? And they has to be connected through some metal lines. So that is called the metal layer 1, right? Now, this MOSFET has to be connected with another MOSFET. How do you connect it? You have to take types of another flyover, means overbridge, right? Type of thing. Go to another height, make a bridge from here, go there, put it there. So that become metal layer 2. Like that, in current manufacturing technology, at least 7 to 8 metal layers are there. Okay, one after another. So that means what I am trying to say is that, see, if these are your devices, say this is NN and say this is PP. So this is NMOS, PMOS. And let's say this has been isolated from each other by trench isolation, right? Now this has to be connected, right? And here also this gate has to be connected, right? So these are like metal layer ones, right? Okay. Now you say, think about here also some devices are there. You need to connect this gate with the gate layer here. Then you should have one more line above by connecting this. You cannot connect everything in the same level, right? You think about, this flyovers, right? Right, when one flyover crossed by another flyover, what either you have to go down or you have to go up, right? You cannot go in the same height, right? So the same thing here. So this is that metal layer 1. So by the separation of this metal layer 1, then people say this separation is called pitch. Okay, say this separation is 200 nanometer, right? Then they call it pitch is 200 nanometer, and the technology node is 100 nanometer. Technology node is half of pitch. Okay, so that's how industry has cleverly, changed their nomenclature from time on. From earlier gate length, then the pitch. Pitch, you understand, right? Pitch is what. Then something more, even more interesting happened. When you have arrived to this 22 nanometer, 10 nanometer, even this does not represent any physical dimension. These are just numbers. Say for Intel 10 nanometer, maybe the same dimension or almost similar dimension for TSMC 7 nanometer node. Okay, so nowadays this 7 nanometer, 10 nanometer does not represent any physical dimension. Okay, it is just an type of reference. Earlier this company, suppose if you are you cannot compare Intel 10 nanometer with TSMC 7 nanometer. Now you have to compare Intel 10 with Intel 16 or Intel 18. You understand? Because now there is no physical relation between one company to the other company, because it is not bound. There is no relation between them. Fine. So that's what it is written here. See, historically, the process node names refer to the number of different features of transistor, including the gate length as well as this metal 1 half pitch, right? More recently, due to various marketing and this discrimination among foundries, this number itself has lost the exact meaning once it used to help. Okay, recent technology nodes such as 22 nanometer, 16 nanometer, 14, 10 nanometer, they are purely and specific generation of chips made in a particular technology. It does not correspond to any gate length or any half pitch, right? Nevertheless, the name convention has stuck, and that is what the leading foundries call their nodes. Okay, right? So you understood what do you mean by technology node, and really the 7 nanometer does not mean the gate length is 7 nanometer, right? Huh? No, physically they are improving, but it's not type of only by gate length. There are different other techniques are also associated. For example, now transistors are not planar. Transistors are type of 3D, FinFET. Okay, this transistor, I think you can recognize, right? This is used to, but can you recognize that this is also transistor? See here, this is the gate. Here transistors are now like this. Gates are like this. Transistors are like a fin. No, fin you understand, right? This is a fin. And the gate will come and go like this. This is source, this edge is drain. Okay. So reduce the dimensions. Yeah, there is a question like, are we also trying to reduce the dimension? Yes, we are trying to obviously reduce the dimensions, but no, not to the same extent. Okay, that we can do earlier. But now the features, now it is more type of, some type of more power efficient. This type of design is coming more and more, right? And if you make the device that small, so many non-ideality factors will also come. Suppose mobility will degrade drastically. Okay, how you can retain that mobility? All these challenges will come. For example, you see, this is here, this is a glimpse of this Intel's. Actually, this is Intel. This is this Intel's 90 nanometer technology node to 22 nanometer technology node. It shows, okay, and here it started with 2003, and then it is 2011. So you see the rapid change, and you will surprise, okay, when I will discuss this. See this in 2013. Oh, sorry, 2003. In 2003, this Intel has introduced this silicon germanium strained silicon gate. Here, what they do is that you see this source and drain region, right? It is no longer silicon. Earlier, it used to be heavily doped silicon, right? Either N++ or P++. It is heavily doped. But now they have changed it completely. They have made it silicon germanium, because silicon germanium has different lattice constant. Lattice constant means, you understand, right? The difference, separation between two atoms, that thing, compared to silicon. So like, you understand what I'm trying to say. Suppose this bench can accommodate 5 students. If I now add one more student, then what will happen? It will create an type of pressure, like stress for those who are sitting in the middle. So that type of, you can see this stress has been marked here, right? And that will improve the mobility and all these things. Okay. Then in 2005, Intel has launched 65 nanometer technology. See, only after 2 years, right? And here is the second generation silicon germanium strained silicon. The same thing. The structure is little bit changed, but typically, see, the silicon germanium is still here, right? Okay. This is up to 65 nanometer technology. Then in 2007, after another 2 years, they have launched 45 nanometer. Can you multiply for 65 into 0.7? 65 into 0.7? 45.5, and they have made 45 nanometer. So you can see this importance of 0.7 is still valid, right? Okay, and hopefully you can also see it here, right? So 45 nanometer, here they have what they have done. Okay, before that, let me tell you one more thing. Here, this oxide used to be silicon dioxide. You know that, right? MOSFET, metal, not metal. Here it is polysilicon. You remember? We always have the not metal, it is the polysilicon. So here also it is polysilicon. Here also it is silicon dioxide as this one. But there is a major shift from 2005 to 2007. Here, what they have done, they have used the metal gate. So this gate is metal. So now the name, which is metal oxide semiconductor field effect transistor, this is again valid because now the transistor has metal gate, right? And in fact, when transistor was first fabricated during its initial earlier जमाने में, पुराने जमाने में transistor में वही metal gate ही हुआ करता था, right? So that's why the name has come metal gate. But in between, for a very long time, we have used polysilicon. Then again, 2007, with 45 nanometer technology, Intel has introduced metal gate. Because what will happen to the polysilicon? See, polysilicon is heavily doped, right? So heavily doped material you can consider similar to the metal. But is it really a metal? No, because if you have some voltage, then whatever be the higher doping concentration you use, there will be at least small amount of depletion layer, right? Right. And as the devices are shrinking, TOX is also shrinking. So TOX become 1 nanometer, depletion layer become 1 nanometer. We cannot use it. You understand my point? When earlier TOX used to be 10 nanometer, तब depletion 1 nanometer होता तो हम ठीक है, मतलब 10% तो वो तो हो जाता है. But when this depletion of polysilicon has become comparable to that of TOX, then we cannot use polysilicon gate anymore because COX is very important. ID, remember, ID is proportional to COX. If oxide thickness is more, current will be lower, right? So the scaling will not work, right? Okay. Then the another thing that they have introduced here is called the high K. So high K means for silicon dioxide, epsilon is 3.9. Okay. High K, say hafnium dioxide has epsilon around 25. So what is the advantage of this? What is capacitance? C is equal to epsilon A by T. Right. So if this is so high, then what will happen? This will become also very high. Right. At the same time, you can do one more manipulation. The manipulation is as you scale down, your oxide thickness become thinner, thinner, thinner. Thinner the oxide, higher will be the leakage current, tunneling current. Right? Thinner oxide, higher tunneling current. Right? But here, what you can do, you can probably increase the T little bit. Because here you have epsilon is so high. Are you getting my point with silicon? Not getting? Okay. See this gate capacitance. Okay. It is epsilon A by thickness. Say the area is same. So we will remove this area. So it is basically epsilon by T. Okay. Now for silicon, it is 3.9 and say 1. Okay. Now we'll try to retain this value only. Okay. Here what we can do, here we have hafnium oxide is 25. It is around 4. So suppose if we make it like 5. If we make it 5, TOX, this is TOX, right? If we TOX make it 5, then what will happen to the CG? It is still compatible, means when actually higher, with this number it is higher. So you are not losing anything in terms of the gate control. But what you are gaining is that now you have thicker oxide. So thicker oxide means less tunneling current. Less tunneling current means your device will become more power efficient. So from this, I think you can understand one thing, that you should appreciate the researches in the material also, because if there were no research in the material, only if everybody is working in the design, then this technology would have not been developed, right? And there was so many research has been going on, right? How to improve, how to change it, and how to do all these things, right? And see here, in 45 nanometer technology also, people have used the silicon germanium source and drain. Okay, even that has continued in this. See, this is the second generation, same technique, but with minor improvement. This is the major improvement. Then another one more shift after 2 years from here. This is another big jump. then people have understood that, we cannot make this gate length smaller, 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 and smaller. Why so? Because you have to always consider this thing. You have source, you have drain, right? See, now you are keep bringing these two closer. This is P silicon, right? You have some depletion layer. So when you are making them closer, 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 at one point of time, what will happen? This two is bound to merge. You cannot restrict this by making this Na higher, because there is another challenge. If you make Na higher, then what will happen to the mobility? Mobility degrades when impurity scattering. You read, right? Impurity scattering. Because of impurity scattering, then the mobility will degrade. So that, again, from the mobility point of view, we are restricted towards this lateral, this lateral dimension scaling. So then the next technique has come, which is called the tri-gate technique or the FinFET technique. Here you can see these are the gates. These are the gates. And this in between these lines, okay, these are the silicon strips. Maybe if time permits, not today, I will show you some better diagram with some schematic diagram. This is an actual diagram. Okay, it looks complicated, but if you have some schematic diagram, it will, then after that you can correlate with this. Okay, but remember, now the transistor is no longer flat, source, drain, gate. No, it is like this. Gate is coming like that. It is now completely 3D. Okay. Then even for 5 nanometer technology node, people found like this type of fin structure is also not sufficient. Then what they have to do? They have to use this nano structure. Means you have this type of silicon rods, okay, and gate everywhere. You are getting my point? This is suppose the silicon rod, and then you have the gate like that all around. Earlier the gate used to be, you are getting my point, right? Earlier the gate used to be like this. This is suppose, this is my hand. Gate used to be like this on silicon. This is a silicon fin, but now that has become like this. This is the gate all around. Gate all around. Okay, so that's how the technology has evolved from time to time. Just one small thing here. See the why silicon has introduced 2003 this technique, which is called strain silicon technique. That is because when you introduce silicon germanium, because of this lattice mismatch between silicon and silicon germanium, it will create an stress. Okay, it will create an stress and make the mobility of PMOS higher. See, hole mobility is always low, right? So to improve that, what they tried is that just introducing silicon germanium for PMOS. Okay, but what they can do for the improvement of NMOS? Okay, they have used silicon nitride passivation. You can see it here. High stress silicon nitride film they have deposited here. That will create an stress. So see here. Here the direction of stress is like this, right? It is basically type of compressive stress on silicon. Compressive stress on silicon makes hole mobility higher. Tensile stress, on the other hand, on silicon makes the electron mobility higher, right? So now you think that these two are sitting side by side when you have CMOS, PMOS, NMOS. So for one, silicon germanium source drain, for the other one, create compressive stress, for the other one, create the tensile stress to make the mobility of electron higher, right? And you can see like for 2003 on itself is the oxide thickness was 1.2 nanometer. 1.2 nanometer. So how many atoms in 1.2? You can count, right? Right? Only few. So the silicon, the channel is been separated from the gate by only few atoms of like silicon and silicon dioxide, means the silicon dioxide. Silicon dioxide cannot be atom, right? I mean, it is basically an your molecule, right? Silicon dioxide is molecule. So by that silicon dioxide, the structure, and it is only 1.2 nanometers, means 12 angstrom, right? But that's why, there was no choice, but they had to introduce the high K, because otherwise the leakage current, even at 2003, even in this technology node also, leakage current were pretty high. As a result, there are power dissipation, on-state power dissipation, off-state power dissipation. For these devices, it used to be like off-state power dissipation is dominating, not the on-state. Okay, we have seen on-state power dissipation, right? And that switching loss and all this loss. But for this type of devices, because now you are considering so many devices, if they are off, then there will be like billions of transistors, they are off. If the leakage current is suppose very tiny also, then the power dissipation combining for the total microprocessor or the total circuit is huge, right? So then with this, we'll stop.